Hello everyone, I'm Chun-Wei Shu from Andes Technology. Today I will talk about how to bring Multicore RISC-V and the Zephyr RTOS together. It's about our work of RISC-V SMP support of Zephyr RTOS. This talk will split into 4 parts. First, I will give an overview about Zephyr SMP RTOS and the RISC-V SMP processors. Then, I will talk about RISC-V SMP porting of Zephyr RTOS. Third, we'd like to share some experience of SMP synchronization mechanism we use in the SMP porting. Finally, I will talk some future work of our RISC-V SMP support. Okay, first, I'd like to share the current status of Zephyr SMP. Zephyr has started to support SMP from 3 years ago in version 1.7 on the Extensa architecture, and currently, Zephyr 2.7 supports SMP on 4 architectures, but it doesn't contain RISC-V architectures. Thus, Andes has ported RISC-V SMP support on Zephyr 2.7. Our porting is available on both 32 and 64 bits RISC-V SMP processors. For example, it supports Andes 45MP and 25MP processors. Then it's an overview of Zephyr SMP RTOS. The SMP kernel can run multiple threads at the same time on the multiple cores. Besides, Zephyr SMP scheduler is still a priority-based scheduler for RTOS, so it's a high-priority execution-first policy across multiple cores. Zephyr also supports thread affinity feature, which can fine-grain control the specific thread to be executed on the specific core. Then, the locking mechanism used in Zephyr SMP is a fine-grain control spin lock with interrupt disabled. Zephyr core kernel is no longer use the global spin lock. And then Zephyr SMP has basic IPI framework. It provides IPI broadcast feature for scheduling IPI and the syncing state between CPUs. Next, I will introduce hardware feature of RISC-V SMP. The RISC-V SMP processor uses a memory shared across cores, and it usually contains both per-core cache and shared cache. The SMP processor needs an atomic instruction to support exclusive memory access between CPU cores, which is a RISC-V A extension in RISC-V processors. The SMP processor also needs an inter-processor interrupt to notify other cores. The IPI controller of RISC-V is SoC-specific implementation. For example, in Andes platform, the IPI controller is split software. Also, each core in SMP processor could receive and handle the external interrupt, so the external interrupt controller RISC-V click could manage the external interrupt on multiple cores. Finally, RISC-V SMP has a global timer, the global incremental counter to keep the consistent time between cores. Let's go to the second part of talk, RISC-V support of Zephyr SMP RTOS. RISC-V SMP porting contains several changes in the architecture code, like the atomic instruction, booting the multiple cores, and supporting IPI. Also, we need to handle the external and timer interrupt across cores. First, it should boot the slave cores in SMP. We will start the slave core by IPI because the global flag can be used in the XIP mode. Also, slave core should use per-core stack and should initialize CPU local resource. The second one is supporting the per-CPU data access. The SMP kernel contains a CPU array storing per CPU data in kernel, which is frequently used in the kernel context. So Zephyr SMP expects that the architecture there could provide a pointer to this per CPU structure for rapidly accessing in the kernel context. We use RISC-V and Scratch CSR to store this pointer and keep it fixed across many content switches and interrupts. To support IPI in Zephyr, the architecture will implement IPI broadcasting API. Because RISC-V IPI implementation is SoC specific, we will implement it and select kconfig symbol of IPI as a driver layer instead of the architecture layer. The cross-core external interrupt management is via RISC-V PLIC. To support SMP, we should enable and disable interrupt on each heart by default. The special thing of RISC-V PLIC is that it only supports interrupt multicasting. When the external interrupt occurs, each heart will receive the interrupt, but only the fastest heart can claim this interrupt. Other heart will receive the interrupt ID 0 if no other pending interrupt in system. Also, there is one thing to know that RISC-V heart is not equal to PLIC target. When using PLIC, we should map all RISC-V hearts to the PLIC targets. Then, we will provide a cross-core timer, RISC-V machine timer. In Zephyr SMP design, each heart will have a timer interrupt independently to trigger a timer event on each heart. Because of per heart timer ISR design, we need to synchronize the tick counting of multi-heart timer interrupts. Zephyr uses dynamic tick counting from the tick kernel to synchronize the multi-heart timer interrupt. Also, the tick counting should be protected by spin lock. The last one is an optional feature in SMP porting, the uncached memory support in SMP. It is used by non-coherent DNA in the SMP system. We have supported Zephyr no-cache memory feature in SMP, which has no-cache memory section for uncached global data. It is based on Andes V5 programmable PNA. Software can configure the memory attribute by our PNA. Our PNA will use PNP style address matching, and its CSR are hard local. So, to support it on SMP, we will initialize PNA CSR of each heart at the boot time in Andes platform. Then, I talk about the SMP synchronization concept we use in the architecture porting. In the architecture porting, we usually use low-level synchronization mechanism. There are two conditions we should protect our data. The first one is protecting global resource from concurrent access in the multicores. To protect it, we should use a fine-grained spin lock with disabling global interrupt to create a critical session before accessing data. The second one is protecting per CPU data. We should prevent from CPU migration of threads when using per CPU data, so that we don't wrongly access per CPU data of other CPU. In Zephyr SMP, we should disable global interrupt to protect per CPU data access. Let's give some example about them. First, the interrupt disable register of RISC-V PLIC is a global resource. We should set enable register of each heart atomically. Thus, it should be protected by spin lock. The difference in SMP is that using spin lock should consider about deadlock avoidance. The deadlock avoidance is a complex problem, but basically there is a simple advice. When the program holds your lock in this file, avoid to hold another lock from different C file at the same time, if it is possible. The second example is per CPU data example. It is about current interrupt level. The current interrupt level is an individual value for each CPU, so it should be a per CPU variable. If accessing it without protecting, user could get the interrupt level of other CPUs and may mistakenly think that this core is in interrupt. Currently, Zephyr uses the interrupt disable to protect the per CPU data. Finally, there are some future works of our RISC-V SMP porting. The first one is to supporting interrupt affinity feature to assign the interrupt to the specific CPU. The second one is the SMP support enhancement to support Zephyr user mode in RISC-V. Also, there is a problem that RISC-V PMP stackup also use unscripted register, so our SMP porting will conflict to it. This is our talk today. Thank you for listening.